When running a 4160 volts 200 amps feed from an overhead line down a pole to a transformer, it is indeed necessary to run a ground wire alongside the primary conductors. This ground wire serves several crucial functions in ensuring the safety and reliability of the electrical system. Firstly, the ground wire provides a low impedance path for fault current to flow back to the source in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded surface, such as the metal enclosure of the transformer or the pole itself. Without a dedicated ground wire, the fault current would have to find its way back to the source through less reliable paths, such as the earth or the neutral conductor. This can lead to a build-up of voltage on grounded surfaces, creating a shock hazard for personnel and equipment. By providing a dedicated ground wire, the fault current is quickly and safely routed back to the source, tripping the overcurrent protection device such as a circuit breaker or fuse, and energizing the circuit. This minimizes the risk of electric shock and prevents damage to equipment. Secondly, the ground wire also helps to protect the primary conductors from lightning strikes. Lightning is a powerful and unpredictable force of nature that can cause significant damage to electrical systems. When lightning strikes an overhead line, it can induce a large voltage surge on the conductors. This voltage surge can damage the insulation of the conductors, leading to a short circuit or ground fault. The ground wire provides a path for the lightning surge to flow to ground, diverting it away from the primary conductors and protecting them from damage. The ground wire should be properly sized to handle the expected fault current and lightning surge. The size of the ground wire is typically determined by the size of the primary conductors. In general, the ground wire should be the same size as the primary conductors, but local electrical codes may have specific requirements. It's essential to consult the relevant electrical codes and standards to determine the appropriate size of the ground wire for the specific application. The installation of the ground wire is also crucial for its effectiveness. The ground wire should be installed on the top of the pole, as this provides the best protection against lightning strikes. The ground wire should be securely connected to the pole using appropriate hardware, such as ground clamps or bonding straps. The ground wire should be run continuously from the overhead line down to the base of the pole, where it should be connected to the transformer ground. The transformer ground is typically a ground rod or a ground grid that is buried in the earth. The connection between the ground wire and the transformer ground should be made using a low impedance connection, such as a bolted connection or a compression connector. The ground wire should also be grounded to the earth at the base of the pole. This can be achieved by driving a ground rod into the earth and connecting the ground wire to the ground rod using a ground clamp. The ground rod should be driven deep enough into the earth to ensure good contact with the soil. The resistance of the ground connection should be measured to ensure that it is within acceptable limits, as specified by the local electrical codes. In addition to the ground wire, it is also important to ensure that the transformer is properly grounded. The transformer ground should be connected to the neutral conductor of the primary circuit. This provides a path for unbalanced current to flow back to the source. The neutral conductor should also be grounded at the source, such as the substation. The grounding of the neutral conductor helps to stabilize the voltage on the primary circuit and reduces the risk of voltage fluctuations. The grounding system should be inspected regularly to ensure that it is in good condition. The ground wires and connections should be checked for corrosion, damage, or loose connections. The ground rod should be tested to ensure that they are still providing a good ground connection. Any problems with the grounding system should be repaired immediately to ensure the safety and reliability of the electrical system. It's crucial to remember that proper grounding is essential for the safe and reliable operation of any electrical system, especially high voltage systems like the 4160 volts overhead line. Failure to properly ground the system can result in electric shock, equipment damage, and even fire. Therefore, it is important to consult with a qualified electrical contractor to ensure that the grounding system is properly designed and installed. They can assess the specific requirements of the application and recommend the appropriate grounding methods and equipment. They can also perform regular inspections and maintenance to ensure that the grounding system is in good condition. In summary, when running a 4160 volts feed from an overhead line to a transformer, a ground wire is absolutely necessary. It protects against faults and lightning and must be properly sized, installed, and maintained according to electrical codes and standards. Consulting with a qualified electrician is crucial for a safe and reliable installation. Firstly, grounding ensures safety by providing a low impedance path for fault currents, protecting individuals from electric shock and preventing equipment damage. Secondly, it provides lightning protection by diverting surge currents to the ground, protecting the transformer. Thirdly, running the ground wire from the overhead line down the pole to the transformer ground creates a continuous path to earth. This ensures that any fault current or lightning surge will have a direct path to ground, minimizing the risk of damage or injury. The ground wire should be the same size as the primary conductors. This ensures that the ground wire can handle the full fault current or lightning surge. The ground wire should be installed on the top of the pole. This protects the ground wire from damage and makes it easier to inspect. The ground wire should be connected to the transformer ground at the base of the pole. This provides a direct path to ground for fault current and lightning surges. The ground wire should also be grounded to the earth at the base of the pole. This provides an additional path to ground for fault current and lightning surges. Grounding the transformer is crucial for safety, lightning protection, and voltage stabilization. Grounding helps protect against electrical shock by providing a low impedance path for fault currents. In the event of a fault, the current will flow through the ground wire back to the source, tripping the circuit breaker or fuse and energizing the circuit. Grounding provides a path for lightning surges to flow to ground, protecting the transformer and other equipment from damage. The ground wire should be connected to the transformer's grounding electrode, which is typically a ground rod or a ground grid buried in the earth. Grounding helps stabilize the voltage in the electrical system. This is important for ensuring that the equipment operates properly and that the voltage does not fluctuate excessively. Grounding is required by electrical codes and standards. The NEC specifies the requirements for grounding electrical systems. Proper grounding is essential for the safe and reliable operation of electrical systems. It is important to ensure that the transformer is properly grounded and that the grounding system is properly maintained. The ground wire must be properly sized to handle the available fault current. Refer to NEC Table 250.122 to determine the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device protecting the circuit. The ground wire should be copper or aluminum and must be installed in accordance with NEC Article 250. The ground wire should be connected to a grounding electrode system that meets the requirements of NEC Article 250. The grounding electrode system may consist of a ground rod, ground plate, or other approved grounding electrode. The resistance of the grounding electrode system should be measured to ensure that it is low enough to provide adequate grounding. The NEC requires that the resistance to ground not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional grounding electrode must be installed. The ground wire should be protected from physical damage. The ground wire should be installed in a conduit or other protective covering. The ground wire should be inspected regularly for damage or corrosion. If any damage or corrosion is found, the ground wire must be replaced. Proper grounding is essential for the safe and reliable operation of the electrical system. Ignoring these guidelines can lead to dangerous situations and equipment failure.